A modern database engine processes thousands of read and write requests every second. Data streams collide and interleave continuously inside the central processing pipeline. If a database processed these requests one at a time in a single file queue, the system would stall under the load. Parallel execution is mandatory to maintain processing speed. But executing transactions simultaneously creates a fatal vulnerability. If one user writes to a data item at the exact millisecond another user is reading it, the operations interleave. Transactional isolation breaks down, causing the system to read partial states or log incorrect values. To operate safely, the database engine requires a strict mathematical mechanism to sequence these overlapping operations. Without it, the database will inevitably overwrite and corrupt its own records. The database records this chronological timeline of interleaved read and write operations as a schedule. This diagram compares two timelines to illustrate how we evaluate those schedules. We test for serializability. A concurrent schedule is serializable if its execution yields the exact same final state as executing those transactions serially, meaning one transaction completely finishes before the next begins. Achieving this state equivalence is the ultimate correctness criterion for any transaction processing engine. To understand how the database enforces this, we have to define the mechanics of an operation conflict, map those conflicts using precedence graphs, and expose the mathematical gap between conflict and view serializability. Serializability does not restrict concurrency. It mathematically simulates complete transactional isolation while maintaining the raw speed of parallel processing. The fundamental analytical action used to evaluate the safety of a schedule is the swap. This tabular schedule shows two transactions, T1 and T2. Transforming a concurrent schedule into a serial order relies entirely on swapping the chronological execution order of adjacent operations, highlighted here as I and J. The rule for this action is absolute. Adjacent operations can only be swapped if they do not conflict with one another. A conflict occurs under two specific conditions. First, the operations must target the exact same data item. Second, at least one of those operations must be a write. This grid maps the four possible operation combinations between two transactions to identify where those hazards lie. If both operations are reads, they are entirely safe. The order they read the data does not alter the underlying data itself, meaning they do not create a conflict and can be swapped freely. Conversely, read-write, write-read, and write-write operations inherently trigger a conflict. Reversing their sequence changes the value read by the system, or the final value written to the disk, permanently locking their execution order in place. Isolating and identifying these atomic read and write conflicts is the mandatory first step to mathematically prove whether a tangled schedule can be safely unscrambled. If a schedule can be perfectly ordered into a serial schedule by only swapping non-conflicting operations, it is classified as conflict serializable. To visualize and test these conflicts across thousands of operations, database engines construct a directed acyclic graph, known as a precedence graph. The rule for drawing edges is simple. If T1 writes to a data item, and T2 subsequently reads or writes that exact same data item, the graph draws a directed arrow from T1 to T2. As the schedule continues, additional operations might cause T2 to conflict back with T1 on a different variable. When that happens, the system draws a return arrow from T2 back to T1. This creates a cycle. The presence of arrows looping back on themselves is a mathematical failure state. It proves the operations are deadlocked in their sequence. The schedule is impossible to untangle, meaning it is not conflict serializable. The precedence graph provides a rigid binary test. By detecting these cycles, databases instantly identify and abort hazardous schedules before they can corrupt the system state. While conflict serializability is highly effective, its strict swapping rules occasionally force the database to reject schedules that are actually perfectly safe. This limitation requires a slightly less restrictive mathematical model, view serializability. This tabular schedule shows a specific edge case where three transactions, T27, T28, and T29, all operate on a single data item, Q. Now, notice the highlighted write operations for T28 and T29. View equivalence focuses on the actual outputs of the schedule. It has three strict requirements: identical initial reads, identical read-write dependencies, and an identical final write operation. The highlighted operations for T28 and T29 are known as blind writes. These transactions write a new value to the data item without ever reading its current value first. Because T29 performs the final write operation to the variable, the blind write from T28 is completely overwritten. It never affects the final state of the database. Because the final output matches, the schedule passes the test for view equivalence, despite failing the strict conflict test. View serializability mathematically forgives these obsolete blind writes. It proves that a concurrent schedule can safely complete even if its atomic operations technically conflict. This nested diagram shows the strict mathematical relationship between the two serializability models. There is a clear hierarchy. Every conflict serializable schedule is inherently view serializable, but as blind writes demonstrate, the reverse is not true. This raises a critical engineering question. If view serializability accommodates blind writes and allows for higher overall concurrency, why do modern databases refuse to use it? The answer is the computational wall. Testing a schedule for view serializability is an NP-complete problem. The time required to calculate it scales exponentially with each additional transaction, crashing the system under its own weight. Because of this, modern database engines rely exclusively on conflict serializability protocols, like two-phase locking and timestamp ordering. Testing a precedence graph for cycles is computationally cheap and can execute in real time. In system architecture, absolute mathematical perfection is willingly sacrificed for computational viability. We intentionally restrict some safe concurrency to ensure the database can guarantee isolation at scale.